This is a brief version of the preceding, which unfortunately didn't get onto the one set of videos, but it got onto the high quality set. So I'm going to summarize what we did there. We simply have x values 0.8, 3, and 6. So and y values that go along with that are slopes of 0.1, 0.75, 2.2. We just graphed the corresponding points here and connected it with a nice smooth curve. Another thing I'll point out is that I said originally I had this labeled as y factor 2.5, the white graph, and the orange graph labeled as y factor 6, and I had those reversed, so I corrected those in the preceding video. Okay, so we get this graph. Now you should, if you haven't already done it, do the graph corresponding to this information. Okay? And you should pause the video and do that without really looking at much of anything else, but here it is. Okay? So we have x values, 6, 3, 1, and so forth. Those are the values, those are the coordinates at which the tangent lines have touched the graph. And we have corresponding slopes of those tangent lines, 0.6, 1.15, and 1.3. So we mark the y scale from 0 to 1.5, x scale from 0 to 6. We locate the points. And on both of the graphs, I'm asserting without proving, and you might think of how to prove it, that both this graph and this graph will go through the origin, the point 0, 0. So I've included the point 0, 0 as well as the 3 points we get from the table. So there's the graph. Now the big deal here is that there's an important difference between the two graphs. This graph is concave up, this graph is concave down. This graph increases at an increasing rate. It increases faster and faster. That means your slopes for the white graph are not only going up, but they're going up faster and faster as we move along the x-axis. Whereas here, the slopes are certainly increasing, get steeper and steeper and steeper, but increasing at a decreasing rate. They're increasing less and less quickly. So this graph then is increasing at a decreasing rate, and it's therefore what we call concave down. So that it appears, and it's not too hard to understand why that is. We have the lesser y factor here. That's going to drive the slopes upward more slowly than if we have a greater y factor. So we get the concave down behavior when the y factor is 2.5. We get the concave up behavior when the y factor is 6. We should be able to conjecture something here. Think about what you could conjecture. What's going to happen if you change the y factor gradually from 2.5 to 6? You're going to go from a graph that looks like this to a graph that looks like this. Okay, so the slope of the tangent line, the graph of the slope of the tangent line will go from concave down to concave up. Now, what happens right between concave down and concave up? Well, right between concave down and concave up, there's straight line. Okay, so if you have a straight line graph, there's going to be some y factor that makes that happen. And what would that y factor be? Can we investigate and find the y factor that gives us a straight line graph when we do slope versus position of the tangent line? Slope of the tangent line versus the position of tangency.